I have added a few drops of each of the ions, or each of the solutions, into test tube 1. You will notice that while I had colors ranging from blue to orange in my original solutions, this is more of a yellow color, which I get from mixing the ions. In this way, I might not be able to know which ions are present simply by looking at the color of the test tube. Your unknown may appear this same yellow color or may look more like the orange, blue, or green of one of the ions that are present. I want to make sure to stir the solutions so that all of the reactions occur for all of the ions and I don't have a layering. This way I can ensure complete precipitation and complete removal of unwanted ions. My first step, much like with the silver group step, is to test for the silver with the hydrochloric acid. As always, be sure to check both the concentration and the label on the bottle. We're going to add a few drops here, and you'll see immediately there's a precipitant. If we were trying to test for lead or mercury, at this point we would want to isolate this and follow the steps from the previous procedure. However, we know that this must be silver. We're going to do a more definitive test by simply dissolving the precipitate and reprecipitating it out, but we're not going to follow through the procedure looking for either the mercury or the lead. When we remove our test tube from the centrifuge, you will notice that the solid has gathered at the bottom, and now we can see it's more white in color than the yellowish color it appeared before. We're going to carefully decant this first supernatant into a new test tube because this contains all of the other ions that we are looking for. This test tube is already labeled number 2, so I can keep track of it. When I decant, I pour slowly and carefully, and you'll notice that this precipitate stays at the bottom. I still have a few of the other ions present, and they may interfere with future tests. So I'm going to add a few milliliters of deionized water, stir this up, centrifuge again, and decant off into a waste container before I test the precipitate for the silver ions. This precipitate in test tube 1 is silver chloride. We're going to make sure that it's actually the silver ions because silver should dissolve when we add ammonium hydroxide. Note that there are also chloride ions present, and these will remain present in the solution when the silver chloride dissolves. The silver chloride won't dissolve completely. You can see there's a little bit of a yellow color, which means I probably still have a few of the other ions present. I don't think that this will affect the results of this particular test. The silver hasn't dissolved just yet, so I will need to stir it with a stirring rod to break up the particles and expose them all to the ammonium hydroxide. With the addition of a few more drops of the ammonium hydroxide and some sufficient stirring, my precipitate has now dissolved. This solution contains ions of the silver complex, ammonium silver +1, and chloride ions. I'm going to see if this is really silver by adding some nitric acid. This will remove the ammonia from the silver and cause them to be able to combine with the chloride and form the silver chloride precipitate once again. As you can see, just a few drops of the nitric acid into the solution causes the white precipitate to reform. This is a positive test for the silver chloride ions. Iron hydroxide is very insoluble. Magnesium hydroxide is also insoluble, but much like with the lead chloride compared to the silver and mercury chlorides, magnesium hydroxide is less soluble than the iron is. So we're going to add a minimal amount of potassium hydroxide, and we'll heat this a little bit in order to try and keep the magnesium ions dissolved into this solution. Make sure that you are grabbing the correct bottle before you proceed. As you can see, adding a few drops of the potassium hydroxide, immediately forms a gelatinous material. Hydroxide has a tendency to form this amphoteric gelatinous material with some ions. This could indicate either the presence of magnesium or iron. Stirring the material may cause the precipitate to disappear. This is why it's important to stir periodically while adding the material. We will need to continue to add drops of potassium hydroxide until stirring does not cause it to disappear. Iron hydroxide is more of a brownish color than magnesium hydroxide, so this color indicates that we probably have the iron hydroxide present. I've stirred this solution so that we can see that that it's reacted completely with the entire solution. I'm now going to heat it for a few minutes in a hot water bath just to try and redissolve the magnesium ions. Once we have added enough of the hydroxide to form a cloudy mixture, we want to adjust the pH so that it is very close to neutral. We can do this by adding in combination both nitric acid and ammonium hydroxide, adding 1 or 2 drops at a time and checking the pH. After stirring, we can check the pH by taking the stirring rod, which now has some of our liquid on it, and touching it to our litmus paper. We can see that this litmus paper is still staying pink, and this litmus paper is turning slightly pink. So this is slightly acidic, but we still have some cloudiness to our mixture, and so we have a little bit of hydroxide ion. I'm going to add 1 more drop of the ammonium hydroxide and then proceed. Test tube 2 contains my iron hydroxide compound that precipitated after the addition of the potassium hydroxide. I want to redissolve this so I can test for the iron in 2 different ways. I'm going to redissolve in the nitric acid. I first just want to add a few drops and stir. If it doesn't dissolve completely, I will add some more drops. There, as you can see, all of the iron hydroxide has redissolved in the nitric acid. There are 2 characteristic tests for iron that I'm going to try here. So I'm going to divide my solution between this test tube, number 2, and test tube 2B. I want to have roughly equal amounts, but it doesn't need to be exactly equal. The first test that I'm going to do is to take the potassium thiocyanate and add it to this solution. This gives a dark red precipitate in the presence of iron 3+. As you can see, I've got a blood red precipitate forming in this solution, and that is a positive test for the iron ions. There's another unique test for iron, so I'm going to show you that in the other test tube. Much like the ammonia with the silver, cyanide and thiocyanide compounds, or ions, form complexes with iron, and this is why it makes such a good test for the iron. We are using the potassium ferrocyanide, and just a few drops, instead of turning the iron red, turns it a dark blue color. This is a positive test for the iron 3+ ion. Be sure to dispose of the contents of test tube 2 and 2B into a container marked for cyanide ions and thiocyanide ions. You may find there is some residual material left in the test tube. Please rinse the test tube with a small amount of water and dump it into the same container. This solution contains the supernatant that was poured off of the iron hydroxide solid precipitate. This solution should contain any nickel, copper, or magnesium ions. You'll notice there's a slight blue or green tint to this, indicating the presence of either nickel or copper ions. Both of these ions will, similarly to silver, form a complex ion with the ammonium hydroxide. In nickel The ammonia in nickel and copper, however, will form brightly colored complex ions, giving a darker blue color. This is an indication of either of the two ions being present. We want to make sure that this is mixed thoroughly throughout and that the color is persistent. If we leave it so that it is a pale color, we may not have complexed all the ions and may be unable to do the rest of the reaction. If your test tube returns to a pale blue or blue-green color after adding the ammonium hydroxide, particularly with a faint cloudiness, this is an indication that you're forming copper hydroxide or nickel hydroxide and you haven't added enough of the ammonium. Add a few more drops and continue to stir. Now that we have a dark color throughout, we want to do our test for the nickel ions. The first thing we're going to do is add the dimethylglyoxine. This particular compound complexes also with the nickel, but not with the copper, and forms a dark red precipitate. This is a positive test for the nickel ions. We want to make sure to remove the nickel ions so they don't interfere with other tests. So we're going to stir completely, centrifuge, and decant off the supernatant fluid. At this point, the red precipitate has separated from the blue solution. The fact that the solution is still blue indicates that there's probably still copper present, though we will proceed with its characteristic test. You can either decant off the blue or you can filter. I'm going to elect to filter because it looks like there's some of the red still floating around into the supernatant fluid. This red solid contains nickel, and nickel is not a great compound to have in the environment. So be sure to dispose of any of this red solid by rinsing with small amounts of water into the appropriate waste container labeled for nickel. Now that you have removed the nickel, the test tube should contain a dark blue color indicating that there is copper present. We want to verify that this is in fact copper by using another method to test for it. You may recall that we used the potassium ferrocyanide to test for the iron in the original mixture. However, when iron precipitates, it forms a dark blue precipitate, which would be difficult to see in here. Copper, on the other hand, will form a red precipitate. Make sure you are using the correct bottle, as the compound potassium chromate used to test for lead is very similar in color. As you can see, we're forming a red or brown precipitate at the bottom of the test tube here. We're going to use the centrifuge to separate the precipitate from the rest of the mixture. We want to make sure that the supernatant fluid looks relatively colorless because any blue color would indicate that there is still copper present. I decanted most of the supernatant liquid, and there's a small amount of liquid remaining and some of the solid that is the magnesium, ammonium, hydrogen phosphate precipitate. I want to dissolve this so that I can work with the solution. I'm just going to add 1 or 2 drops of hydrochloric acid, just enough to get this back into solution. Remember that I can test the pH of my test tube by using the red litmus paper. I can take the stirring rod that I've been using to stir and just put a dot onto the red litmus paper. The change to a blue color indicates that this is in fact basic. If we want to determine how basic it is, we're going to need to use some pH paper. This paper is designed so that I can determine the pH in the range of 8 to 9.5. So any color of blue is indication that I have a high pH. As you can see, I have a dark blue color, so this is a high pH. At this point, I'm going to centrifuge this test tube so that I can work just with the magnesium ions and decant off the supernatant liquid. I've decanted off most of the supernatant fluid, and there's just a small amount of the solid left. This solid is magnesium ammonium hydrogen phosphate. I want to work with the magnesium ions, so I'm going to dissolve them using hydrochloric acid, but I want a minimum amount of the hydrochloric acid in there, so I'm only going to add a drop or two, just enough to get it dissolved. You'll notice the white smoke coming out. The chloride in the hydrogen chloride will combine with the ammonium to form ammonium chloride. This compound will form a white smoky material. Simply shaking it up dissolves most of the solid. I'm going to take a stirring rod to complete the dissolution process. Now I'm going to try and form simply magnesium hydroxide ions. I'm going to do this by adding potassium hydroxide. You can see that I'm forming a solid again. I'll hold it against the black background so you can see better. So I've got that precipitate in there. So now that I have a good precipitate, I'm going to try and test it with resorcinol. Resorcinol should turn this a blue lake color. It may appear purple due to some presence of a little bit of the remaining potassium ferrocyanide, or just a violet color that comes through with the same process. So you can see the top part is a little bit gray, and we're starting to get that violet color in there. As I shake it up, you will see more of that blue or violet color coming through. It's called Blue Lake because it's actually in the precipitate, not the solution, that we see the color, but the precipitate doesn't tend to gather at the bottom, so it's suspended as color seems to be suspended throughout the lake. This is a positive test for the magnesium ion.